In this video, we are going to sketch the transfer characteristic of this network, meaning we are going to sketch the output and the input. So the output as a function of the input voltage. Okay, so the input voltage is a sine wave. So what we are going to do first is to find the output voltage, and then with the expression that we obtained for the output voltage, we'll be able to sketch the transfer characteristic, which is the output plot versus the input voltage. Okay, so the plot on the right here is the IV characteristic of the diode. So the diode starts conducting when it reaches this threshold voltage that I will call VD on, and then below that threshold voltage the diode is off, right? So the diode is off, and above that threshold voltage the diode will be on. So we can approximate this by this curve. Now, so in this case, I will so let me sketch the diode here. So the current is ID. The voltage across that diode will be VD on, and when the diode conduct, as you can see from the characteristic, ID will be positive. So the current to the diode will be positive when that diode is on. So I can replace the diode by this voltage, which I call VD on, and the current to the diode will be ID. So I am going to find the output voltage, which is going to be a function of the input voltage, because the input voltage must have some values to be able to turn the diode on and off. So the diode has two states, whether the diode is on or the diode is off. So to be able to find the transfer characteristic, I'm gonna start with when the diode is on. So I'm gonna assume the diode is on. Okay, so in that case the current to the diode will be positive. Okay, so if this assumption wasn't correct, then I'll end up with the current of the diode, the current to the diode not positive. Okay, so the input voltage is a sine wave that looks like this. So let's take the sine wave over a cycle. So let me draw it a little better. The input voltage over a cycle. So let's say that I have something like this, and this is a Vmax, and that will be minus Vmax. So the input voltage, the must be at least bigger than VD on to be able to turn the diode on. Okay, so VI here. So this is time. So what I'm going to do, I'm going to draw the network, and because I assume that the diode is on, I am going to replace the diode by voltage source, and the current to the diode. If the diode is on, we call it VD on, as ID, and the voltage across that diode will be VD on. So we are going to find the voltage across the resistor. Okay, so for this videos, I'm mostly going to use KVL and KCL to solve this network. So I'll write KVL following this loop. So that means VI will be equal to VD on plus R times ID, right? So this implies that ID equal to VD on, VI minus VD on divided by R. So the condition or the assumption that we made at the beginning, saying that the diode is on, that means ID is positive. So this implies that VI minus VD on must be positive, and this gives me VI bigger than VD on. So from the analysis that we just did, diode on, when VI is bigger than VD on. Now, what is the output? So let's write the output equation. So we know that the output is R times ID. So the output will be VI minus VD on, right, from what we derive above, right? So that comes from here, right? Okay, so then for this case, I call it case number 1. The output voltage is equal to VI minus VD on, so that the voltage across the diode when VI is bigger than threshold voltage. Now, when the diode is off, let's misspell diode here. So diode is off, then that means we have this scenario where the diode does not conduct. So I mean there's no current. Current is 0. So that's V0. So in this case, ID is equal to 0. So the voltage V0, which is R times ID, is equal to 0. So for case number 2, what do we have? We have V0 equal to 0 when VI is less than VD on. So when we put it together, V0 is equal to 0 when VI is less than VD on, and then it is equal to VI minus VD when VI is bigger than VD on. Now I can sketch the input voltage and the output voltage on top of each other. So for the sake of so let me use a different color, which is I can use this. So let's say the input voltage is given by this. So let's put video on this graph. So let's say this is video. So when the input voltage VI is bigger than, so VI is bigger than VD1, then the diode will conduct, otherwise the diode will be off. So for the voltage, that is less than VD1, right? So the VI is less than VD1, so that means the voltage, the output voltage is 0. Then when it reaches VD1, then the diode will conduct, so the output will be equal to VI minus VD1. So at the maximum we have Vmax, so we have Vmax, right? Vmax minus VD1. So the voltage will be this, and then when we reach this point, it's gonna be off again. Okay, so let me sketch it a little better, like that, and then it's gonna remain off, right, when up to that point. So up to this point, it's off up to that point. Now, so this is our output voltage, so that's V out, right? V out. So, and this is time, so this is T. So what I'm going to do now, I'm going to sketch the output, the transfer characteristic, meaning the output as a function of the input voltage. So I'll put the input voltage VI here, and then I'll put VL here. So we know that V out is 0 up to VD on. I'll put a 0 up to VD on, and then when it reaches VD on, V out equal to VI minus VD on. So it's like Y equal to MX plus B. So the B is minus VD on, the M is equal to 1. So the slope M, right, is equal to 1. So that means when I sketch this, the graph will have slope 1. Okay, so the slope is 1. So that is VI. So that's the transfer characteristic, I mean the output voltage as a function of the input voltage. Okay, now let's assume that we change the direction of the diode. So we still use the same characteristic, and this is what we call a VD on. So in this case, we have, so I should like put the polarity as this. It's a sine wave, so we're gonna consider the positive cycle first, and then the negative cycle next. So now in this case, we have, so we're gonna also assume that the diode is on. So diode on, right, to find the relationship between the output voltages, the condition that the input voltage must meet, so that the input voltage is now 0, or the diode will be on. Okay, so we have the diode on. So the diode, look, I'm gonna sketch it. We have VD on, the diode is on. So I can replace it by I will replace it by this voltage source, right? So the diode, so let me draw it. So the diode excuse me, so diode excuse me, the diode looks like this, and the current ID is that way, and the voltage VD on, right? So, and the current ID will be in that direction, and then we have the resistor R, and we still have the voltage across the resistor. So this is VI. So when we have VI, so let's still write a KVL. So to be consistent, I'll go around the loop like this still. So minus VI minus VD on. This is VD on. Okay, and then minus RID equal to 0, because we're moving against the current, so the voltage drop across the resistor is equal to negative ID times R. Okay, so if you know, if you apply Ohm's law, you have V0 will be equal to negative R times ID, right? So that's what I have in there. Okay, so VI will be equal to so we wanted to find a condition under which the diode is on. So we have minus VI minus VD on, that's equal to RID, and then diode on. So when the diode is on, what do we have? We have ID is positive, R is positive, so that means minus VI minus VD on must be positive. That means VI is less than minus VD on. So when VI is less than minus VD on, then the diode will be on for that condition. So for under this condition, we have diode on when VI is less than minus VD on. And then what's the output? V0 is negative RID. So that is equal to VI plus VD on. Okay, so let's then the diode will be off. Okay, the diode will be off when VI is bigger than minus VD on, and in that case there's no current. ID equal to 0, so VL, which is minus RID, will be equal to 0. So when I put it together, I will have, the color is not good. So when we put it together, I will have V0 equal to 0 when VI is bigger than minus VD on, and then is equal to VI plus VD on when VI is less than minus VD on. Okay, so in that case, we have this. So let's sketch. Let us sketch the output and the input in the same. Okay, so the bottom piece doesn't look too good, so maybe something like this, that's better. So this is VI and this is time. So we sketch it over one period. Now when I have the output, so what is minus VD on? So minus VD on will be here. So when VI is bigger than minus VD on, the output is 0. So up to this point, VI is bigger than minus VD on, so it's 0. Then also here, VI is bigger than minus VD on, so it's 0. So then in this area, the diode will be on, and so here that will be, so the minus V max, right, plus VD on. So VD on is positive, so the amplitude is slightly less than. Okay, so that is the voltage across the diode over one cycle. Now let's sketch the transfer characteristic. So I'm going to sketch the output as a function of the input. So the input is here, the output is here. Now so when this is minus VD on, which is the minus VD on, okay, so when it's bigger than minus VD on, when VI is bigger than minus VD on, then the output is 0. So the output is 0 when VI is bigger than minus VD on. So let me use this color. It's bigger than minus VD on. Okay, the output is 0. Then when the when VI is less than minus VD on in this condition, right? Minus VD on. So I mean that's here. So let's sketch it with this color instead. I think it looks better. Now the slope, so V0, so let me write it there. So V0 equal to VI plus VD on. So the slope is 1, right? That's the slope. That's M X plus B, right? So B is a VD on. So I'll have VD on here. So the graph will have a slope 1. Okay. So well, if I prolong, that's how it's gonna look like. So the slope 1. So the output voltage plotted as a function of the input voltage looks like this. Okay, so that is the transfer characteristic.